Okay, so what we have been looking at is the problem Ax is equal to b. We want to solve this problem Ax is equal to b. That is the objective that we have set up with. And we already know existence uniqueness, that is done. We already know one method to compute the solution of Ax is equal to b, which is edu decomposition. And now what we are discussing, we are discussing QR decomposition based method, right? So we are discussing QR decomposition of A and how QR decomposition can be used to compute the solution of Ax is equal to b. So we saw that if you do QR decomposition, so you write A is equal to QR. So what does that mean? Q is an orthogonal matrix. And R is an upper triangular matrix. Okay, so while this thing can be done for a rectangular matrix as well, what we are doing is, for simplicity, let us assume n by n case. Okay, square matrix case. So right now we are only restricting ourselves to square matrices, but we'll see later on that we will be able to do this for rectangular matrices as well. Okay, so we'll do that because our important application, the least squares application, will always have this rectangular matrices. Okay, so that is something that we have. So QR decomposition of A is equal to QR, Q orthogonal, and R upper triangular. Okay, so suppose this is the setting that we have. Then Ax is equal to B. I hope all of you remember. I can write down QRx is equal to B, which implies that Rx is equal to Q transpose B. And this can be solved by back substitution, right? So backward substitution will let us do this. So if you are able to find out matrix Q and matrix R with this property orthogonal and upper triangular, then A is equal to QR. And one thing that you can convince yourself, is this QR decomposition that we are calculating is actually nothing but Gram-Schmidt orthogonalization. Okay, so Gram-Schmidt, yes, Gram-Schmidt orthogonalization. Okay, so this process is actually orthogonalizing. So if you have a matrix A whose columns are linearly independent, that means that rank of matrix A is full, then the columns of A actually form the basis for the entire space Rn, right? And what you are having in Gram-Schmidt orthogonalization is that you can orthogonalize the given basis into an orthonormal basis, and the columns of Q, actually the orthonormal vectors, precisely do that. And there is another condition in Gram-Schmidt orthogonalization process which says that you form this orthonormal basis not in an arbitrary way, but you form it in a way such that the first vector in the basis and the first vector in orthogonal basis span the same space. That you can see here through the upper triangular structure. First two elements in basis, first two elements in orthonormal basis, they span the same space, and that's how you construct this particular basis. And you see, because of the upper triangular structure present in the matrix R, that is precisely what is happening. So when you multiply Q to R, where R is on the right hand side, you see when you multiply Q to the first column of R, the first column, only the first entry is non-zero, all other entries are zero. That means that you are only multiplying the first column by that non-zero entry. That gives you first column of A, right? So if you see this relation, you will realize that you are increasing the spans like the columns of A, right? So that shows this process actually is Gram-Schmidt orthogonalization process. So this is a lot of hand waving I have done, but you can convince yourself by writing down those equations and verifying those equations. Okay, so this is something that you can verify for yourself. Okay, so yesterday we started. We understood the importance of QR decomposition and how is the help that we will get through this particular thing. So there is another issue that we said, multiplying by orthogonal matrices. You have a very nice property. The property is that it does not change the length of the vector in the range space, as well as it preserves the angles between the vectors in the domain space, right? So if there is some angle alpha between the vectors x1, x2, when you apply q on it, then qx1 and qx2, whatever be the image vectors in the image space, they will still have the same angle between them. So orthogonal matrices preserve the angle and the length of the vectors upon which they are acting. We saw an example yesterday where we saw there is a drastic change in length and angle between the vectors possible by action of it. But orthogonal matrices will not do such a thing. Okay, so that's why these orthogonal matrices will be nice matrices. If you multiply by them, there is no numerical instability creeping in. That's why that is another important reason why you want to work with orthogonal matrices. Okay, so backward stability. The multiplication by an orthogonal matrix is backward stable. That's the statement that we had written down, though we'll not prove it. So these are the several reasons why these QR decomposition orthogonal matrices are really very important. And yesterday we started with rotators, right? So yesterday we started with rotators, and we showed that rotators are actually orthogonal matrices. Okay, so suppose we go into the Rn space. So in the Rn space, now you can see I'll define a matrix. Okay, so how will I define a matrix? So suppose we had the matrix Q in R2 by 2. Okay, so just for the sake of simplicity, I will write this matrix as Q CS minus SC. Okay, so C represents cos theta and S represents minus sin theta. Okay, so suppose I write it down in this short form, then for any matrix Q belonging to R n cross n, suppose I write down the matrix Q like this. Okay, so I have identity here up to identity here, then I have a C here, then again identity, then I have a C here, then I have a S here, I have a minus S here, identity and identity. All other entries that I have not written in this matrix are actually zero entries. This is a n by n matrix, and what is happening here, this is the ith row, and this is the jth row. Okay, and similarly this is the ith column and this is the jth column. So again, what I have done, you see, I started with an identity matrix, and in the identity matrix I only change the row and column number I and j. And how do I change? I just introduce this 2 by 2 rotator, plain rotator. So now you see what I have really done. So yesterday towards the end of the class, while we were discussing, we saw that we constructed a rotator of this type, right? So I think we wrote it down, right, in yesterday's class somewhere. Did we? Yeah, here. So we wrote it down. So here you see I and j. So here I is equal to j is equal to 3. I look at I equal to j equal to 3. Then what I am really doing is that in x1, x2 plane, I am applying the rotator, keeping all other components constant. So the same thing is going to happen here also. Here see only ij. So if you really want to say xi, xj plane, okay, so the rotation is going to happen in the vector which component? Xi, xj. Okay, so the rotation is going to happen xi xj plane, so to speak, right? So that is the plane in which rotation will happen. So what is the meaning of this statement? The meaning of this statement is that when you apply q on a vector x1, x2, xn, so what does this mean? This means that suppose q into x, so what is q? 1 1 c 1 1 c 1 1. Okay, and here I have s minus s, and if I apply this on x1, x2, xi, xj, xn, then what will be the product? Can somebody tell? So if I design this C and S in such a way that I will make xj 0, I will make xj 0 from xi, right? That's the operation that I'm going to do. So what will be the product after this rotator? what will happen? So which are the components that are going to change and which are the components that are not going to change? First, can you tell me that?
Xi and Xj will change.
Xi and Xj will change, all other components will be same, right? So x1, x2 up to xi minus 1. Then I don't know what will happen to xi plus 1 up to xj minus 1. Then I don't know what happens to xj. Then xj plus 1 up to xn. So the only two components that are going to change, let us put them in different color. So this is the place, ith and j. And what happens to this ith and j component? What will be the element here?
xi cos theta minus xj sin theta.
So that will be x root of x
Yes.
square plus xj square. That's what you will have here. And this guy will be equal to 0 because that is how you designed your C and S, right? So if you design your C and S, so you choose an angle theta in such a way that this happens, then you have introduced a 0 here, right? You have introduced a 0 here. And you can very easily check. Okay. So this is something, if you are not convinced, you check Qx only changes ith and jth entry of x. Okay, that is what it does. And in general, if I have a matrix q which is of this type, and I have a matrix A which is a size n by n, then qa, what will qa do? Can you tell what will qa do? What entries in matrix A will be changed by operation qa? So in QA, only ith and jth rows of A will be changed. All other entries in matrix A, all other rows in matrix A will not change, because what will happen? QA basically is QA1 up to AN, right? Column wise you multiply, so you get QA1, QA2, QAN. And you know what happens in QA1? Only ith and jth entry of this vector A1 changes. Similarly for AN, only ith and jth entry of that vector changes. So only ith and jth rows are going to change because of this. All other entries in the matrix are going to remain constant. So if you apply QA, then only these entries are going to change. And once you understand this, then it's very easy to observe. What is easy to observe? So let us write it in terms of theorem. So what does it say? So the theorem says, let A be a matrix in Rn by n. Then there exists an orthogonal matrix Q. Then there exists an orthogonal matrix Q. And an upper triangular matrix R. Upper triangular matrix R, such that A is equal to QR. So you get A is equal to Q. So you can actually do this. And how do you do this? Now the proof is not really very difficult. You already understand the proof, right? So what am I going to do? I'm going to do the following. What is it? So suppose A is the given matrix. Okay, so A11, A21 up to AN1, A12 up to A1N, A22 up to A2N, so on and so forth, AN2 up to AN. This is the matrix that I have. Then consider the first column, A11, A21, A31, so on and so forth up to AN1. Okay, so this is the column that I have. Now I want first to take this column into this form, star 0, A31 up to AN1. So what is the rotator that I apply? You see, I construct the matrix Q such that I denote it Q21. So that Q21 transpose into this is actually equal to star 0, 3, 1. So you understand this 2-1 notation? What is this 2-1 doing? 2-1 is basically looking at first and second row of the matrix, or the first and second row of this vector basically, and it is taking this into this form. Correct? So this is what it is doing. Now what will I do? I will construct a rotator Q31 such that Q31 transpose Now, what will happen to Q31 transpose? So I will maybe write it in red color. So Q31 transpose will convert this vector Q1 transpose this into this. Then what will I do? I'll construct next vector. What will it be? Q41 transpose. Q41 transpose. So what will it do? It will convert it into this star and this zero entry and so on and so forth. So how many such rotators I will require for the first column? The first column I'll Q21, Q31, Q41 up to Qn minus 1, 1.
Minus 1.
Is that right? So these are the number of rotators. These are the number of rotators I require. So and Qn1, right? So n minus 1 matrices I'll require Qn1 transpose, right? So this n minus 1 number of rotators, n minus 1 number will make the first column into 0. But what are we supposed to do? We are supposed to apply this operation on the entire matrix A. So if you apply this operation on the entire matrix A, what are you going to get? You are going to get Qn1 transpose, so on and so forth, Q21 transpose. These are the n minus 1 matrices that you had into matrix A. How does the matrix A gets transformed by these actions? You get a star here and all other entries are 0. And then you have this particular matrix, right? So I'm not really interested in these entries right now. So this is the matrix that you get. And now what will you do? You will focus onto this entry now. You will focus onto this entry and then you will construct how many? N minus 2 rotators such that these guys will turn into 0. And you will keep on doing this operation until the last one, this guy, n minus 1 becomes 0. So 1 rotator. So for this column, you require n minus 1 rotators. For this column, you require n minus 2 rotators. And in the n minus 1th column, you require n rotators. So these are the total number of rotators you will build. And using this total number of rotators, what will happen? You will eventually convert the given matrix A into that matrix. And now you see this big chain that we have here. So this big chain, you can take it onto the right hand side. And when you take this big chain onto the right hand side, you get the orthogonal matrix Q that you really wanted to construct, if at all you wanted to construct. If you are trying to solve the system of linear equations, then what you are supposed to do, you are not supposed to do anything. You have an upper triangular matrix. So if you want to solve okay, so this is the proof. Okay, this completes the proof. I have not written it down, but I have orally completed the argument. Do you understand the argument how you will calculate QR decomposition? Is this clear to everybody? How do you calculate QR decomposition? And what you're supposed to do when you are really solving a system of linear equations Ax is equal to B is that you do not need to calculate QR decomposition explicitly. You don't need to multiply all these rotators together in order to calculate QR decomposition. What you will do, you will apply all these rotators here one by one, right? Q21 transpose, Q31 transpose, Qn1 transpose, then you will have Q32 transpose, and so on and so forth. This chain of rotators will have, you will have Ax here, and this B that you have here, you will apply the same operation here also. So Q1 transpose, Q31 transpose, Qn1 transpose, Q32 transpose, and so on and so forth. So you'll apply same operations on B also at the same time. What will it happen? So this is like you are assembling QR decomposition. You are not actually calculating. You don't need to multiply these matrices together explicitly because you don't want to see the matrix Q, so to speak, right now. If somebody tells you I want to see the matrix Q and I want to see the matrix R such that A is equal to QR, then you will have to multiply all these matrices together, right? So that is something that you will have to do. But right now you don't want to worry about that because that is something that is not required for you. Just do these operations, then this whole operation gets converted to R. You have X as is, and you get this B tilde. This B tilde is basically nothing but Q transpose B. And once you have that Q transpose B sitting over there, then your job is done. Then you just do back substitution, and you solve the system of linear equations, right? So this is how you will solve system of linear equations using rotators by introducing zeros. You do not need to explicitly calculate QR decomposition. So no need to explicitly calculate QR decomposition while solving Ax is equal to B, correct? So there is no need. You can just do these operations, the rotator things repeatedly, and you get the result that you want. So this is something about rotators. So is the discussion clear, like what we discussed and how these rotators can be used to build this thing?
Sir, but we still need to multiply them in order to compute B tilde and R, right?
Yeah, but you don't see that's okay. So that is what you have to understand. So if you are, so the advantageous situation you are in is that suppose you have a b x, right? This is the multiplication that you want to do. So q1 q2 will take q1 q2 itself, q1 q2 and x, or q1 q2 into b. Suppose that is the multiplication that you want to do. Then how many number of floating point operations you are required to do in order to calculate the matrix product? Do you know that? Have you seen that lecture that I have
This
shared?
cubic, this cubic, like it's been in
Cubic. So it is n cube. And how many are required in this operation? Matrix vector multiplication. It's square, right? It is order of n square. So now you see, if you multiply these two matrices first, and q1, q2, you are required to do n cube number of operations. Is it no?
Yes, sir.
And now you multiply this product with b, that is n square. So anyway, the computation will be dominated by n cube factor. But if you do this q1, q2b, if you do this multiplication first, q2b, how many number of computations will require? N square. And if you do this, then one more n square. So that is 2n square. So the computation is reduced by order of 1, right? Initially, if you do this way, you will require n cube number of operations roughly. But if you do it this way, you will require n square number of operations. And now put in sparsity, you know that only couple of entries you will have to change when you do this operation, right? So you will have a lot of advantage by not explicitly multiplying these two matrices. Okay, q1, q2. You will not multiply the matrices explicitly, q1, q2. You will multiply q2 into b first, then q1 into q2 into b. So this is something that is very important. So matrix multiplication is associative, is something that you all have learned. But that associativity, how does it help? So we have used that associativity many times in our lectures to suit our calculations, right? So कुछ तो adjust करना था तो bracket इधर से इधर हटा दिया. That is the theoretical advantage, but the real power, computational power of that associativity law comes in here when you decide the order in which you will multiply the matrices, so that the computation that is incurred is very small. It's comparably less, right? So if you see here, the first way you multiply, you get n cube operations. The second way you multiply, you get only order of n square operations. So you have a huge advantage. So you might have seen these type of things really matter. When you have a deep network, you are doing back propagation, you have lots of matrices of different sizes, and now you want to decide which multiplications you will do first in order to save the computational time. What will that save in what will happen if you save that computation time? Your training time of the network will reduce, right? So things like that, these are the important things, right? So these are the things that we have to pay attention to. Otherwise these laws will never make sense to us. Like associative ठीक है हो गया भाई, मतलब where it is used. So these are the places where it is really used. Okay, so this is one clever use where you see that if I calculate this product, then this product, then I'm only doing like n square order operations at a time, right? So this is not as easy as I am telling you. Then you have n minus like almost n square by 2 rotators. So what happens in the computational complexity, you will have to really sit down and work out and see. But this is like the beginning why you don't want to multiply these matrices. Is that okay, Ravi?
Yes, sir, it is clear.
Any other observation here? Okay, in that case, we move further. So since yes,
Sir, one question on the uh,
yes,
on the proof. The proof does not assume linear independence of the columns.
yeah.
Uh,
So actually, yeah, you are actually you are right. So right now you take A invertible, okay. So you take A invertible. So if A is invertible, then the columns are linearly independent, then you don't have to worry. But even if A is not invertible, there is a slight adjustment that we'll need to make, and that adjustment is not very critical. You can very easily do that adjustment, and you can still continue and compute this Q and okay. So there you will use something like you might have seen in your previous linear algebra course, that if you have a linearly independent set, then either that linearly independent set is a basis for the entire vector space, or you can extend that linearly independent set to a basis, right? You must have seen that like result somewhere. So the same idea. If the columns of A are not linearly independent, then you run out of the vectors in the span. Then you complete the basis, and correspondingly those Q will be found out. So there is just a small thing, small addition you can do, but we don't want to get into that right now. So let us say A is invertible. But thank you for this observation. It's a important
okay.
observation.
Thank you, sir.
Yeah, I should have mentioned earlier that A is invertible, but yeah, for non-invertible matrices also you can come up with this. Then R will not be strictly upper triangular, but we will not get into that right away. I think we'll need it later on. At that time, we'll see what we can do. Okay, so if this is okay, then we go to the next case, reflectors. Okay, so what are these reflectors doing? So rotators were rotating, so reflectors have to reflect some, right? So that's like a straightforward case that we have. So again, like the case of rotators, we concentrate on R2 case. Okay, case R2 case. So in R2, what is really happening? So the matrix that we want to construct will be a matrix which is of the size 2 by 2, and we want to construct the orthogonal matrix. Okay, so what we are going to look at? So we are going to look at this. So this is my R2 space, and I start with a line which is passing through origin. Okay, so this is the line which passes through origin, L, a line passing through origin. Okay. This is a line which passes through origin. And what is the operator Q going to do? Q is going to reflect every vector in R2 through this line L. Okay. So I have to construct this matrix Q in such a way that every vector in R2 is going to get reflected through this line. So the first thing first, what I do, I choose two important vectors, okay? Because this is going to be a linear transformation, I am fine with this thing. So I choose this vector, I call this vector V, and I choose this vector, I call this vector U. And how do I choose U and V? So the vectors U and V are chosen in such a way that V is a unit vector meaning vector with norm 1, is a unit vector in L such that every vector in L is a multiple of U. Correct? So basically, this is like unit vector. I have chosen that. And what is U? U is another vector, which is unit vector. But now, what is the property of U? U is orthogonal to V, right? So U is a unit vector in R2, which is orthogonal to L, or orthogonal to V. Correct? So that is what I have. So clearly in this particular case, do you agree that U and V forms a basis? of R2. Do you all agree that U and V form a basis of R2? Now you think what I will do. Now you tell me what I will do. If I have a basis and I have a linear transformation, then what should I do? I should explain the action of linear transformation only on these basis vectors. Because if I understand how this transformation acts on basis vectors, then I know how this transformation acts on all the vectors in R2, because any other vector in R2 is basically a linear transformation of U and V. Is that right? So for example, first tell me what happens to V. So if you see the reflection of V, if you see the reflection of V through the line L, what will happen to vector V? What is the reflection of V through this line? This is exactly same as seeing your own reflection in the mirror, right? So where does this point go to? The reflection of V is V. And what is the reflection of U? What is the reflection of U?
Minus U.
Correct. So this V is V and reflection of U is minus U under this particular thing, right? So what is really happening here? It is very interesting. Okay. Q acts on U and V in the following way. Q of V is equal to V and Q of U is equal to minus U. So for any vector X in R2, there exists unique alpha beta in R such that X is equal to alpha U plus beta V. Do you all agree that this will happen? And then what will happen to Qx? Qx will be equal to Q alpha U plus beta V. That is basically alpha Qu plus beta Qv, which is equal to minus alpha U plus beta V. So what should happen to the vector X, which is alpha U plus beta V? It should become minus alpha U plus beta V. If that happens, then I am through, right? So now I have to construct the matrix Q, which will have this particular action. So what is the aim? So aim is to construct Q with this property. How will we proceed? What will we do? Are you following this discussion so far? Are you understanding what is happening? Is there any doubt about this? Okay, so we want to construct Q with this property. So what do? We do not directly construct Q, but we construct it stepwise. Okay, so construct this matrix P, which is U transpose. So what is the size of this matrix P? What is the size of this matrix P? This is a matrix in R2 by 2 because U is this vector, U transpose is this vector, and you get U transpose. Can you tell what is the rank of this matrix P? Can you tell what is the rank of this matrix P?
One.
Yeah, it's 1, but why is it 1?
Because it's the same column. It's a multiples of just one column. It's multiples of U.
Correct. So if you see it, then the rows like same multiple will repeat, right? So if you can write it down, you can very easily see. So this is rank 1 matrix. Okay, so clearly P is not the candidate we are looking for, because P is rank 1 matrix. You wanted to construct an orthogonal matrix. So the orthogonal matrix is a invertible matrix, obviously, right? Because the columns are linearly independent. In fact, that orthonormal. So P is not a candidate. But why did I construct P? What happens? What is PU? Can you tell me what is PU? PU is P is basically U transpose U. Again, I'll use associativity. So U transpose U is equal to U. Why can I write it down as U? Because I have chosen U to be a unit vector. If U is a unit vector, then norm of U is basically U transpose U is equal to 1. We have said that it's a unit vector, right? So PU actually gives me U. What is Q doing? Okay, Q is not doing exactly that part. That's okay. But what is P doing to V? So Q, what did Q what is Q doing? Here. So Q is sending U to minus U, and P is sending U to U. Okay, almost, except for the sign difference. P and Q are like doing same action on U. Okay, so let us see what P is doing to V. What is P doing to V? U transpose into V, which is nothing but U transpose V. And what is this? What is this? 0. This is 0
0.
because U and V are orthogonal. They are perpendicular to each other, right? So because they are orthogonal, perpendicular to each other, U transpose V has to be equal to 0. So this PV is equal to 0. So what is happening to V? V is going to 0 and U is going to U. U is same and V is going to 0. That's what happened. Wonderful. And here Q is sending U to minus U and V to V. So now can we construct Q from P now? That's the question I'm asking. Okay. Can we construct Q from P? And geometrically first, can you tell me what is P doing, so that intuitively it is clear why I constructed such a P. Intuitively it's clear. Can you tell what is happening? Geometrically, what is this P doing to any arbitrary vector X? Can you tell?
It is taking the inner product along that direction of V.
No. So arbitrarily, so suppose X is a vector, then you write it in terms of alpha U plus beta V, like here. Excuse me. And then when you take action of P on this vector, what will you get?
The projection along U.
Correct. So you are actually taking projection. Every vector that you see in R2, it's actually projected on line L. So this P kind of doing half the job that you wanted to do, right? So that's why it's called orthogonal projection, because along U it is taking projection on L. Every vector in R2 is falling down onto L. And how is it falling down? It is falling down parallel to this vector U. Okay, so that is what is doing. So for example, what is happening? If this is the vector, then it is coming to this vector under the action of P. If this is the vector that you have, then it is coming down here under the action of P. That is what P is doing. Okay, action of P. Because this X will be equal to alpha U plus beta V for some alpha and beta. And when you apply Px, you get alpha U. So you are falling onto that line, this line, and this length is anyway alpha. Okay. So this is what is really happening. So this P is doing half of the job for you. What did you want to do with Q? You wanted to travel the equal distance on the opposite side also, right? You wanted to travel equal distance on the opposite side also. P is taking you halfway there. So can you modify this P slightly? Can you do something to this and you get a Q? That's why I'm asking, can you construct Q from?
Sir,
Can you do? Huh?
we can take like two matrices. Like here we constructed P as UU transpose. We can construct another matrix, let's say, because we have used symbols Q and R, I'll call it T. So if we take a matrix T which is VV transpose, then minus P plus T is basically going to give me.
VV transpose. Okay.
So if I take minus P
Hmm.
plus T, so if I do minus P plus T on U, then I get minus UU because T operating on U will always give 0 and P
Hmm.
operating on V will always give 0.
Correct.
But now I want Q operating on U to give minus U. So I
Hmm.
will negate P and I want T operating on V to always give V.
I understand. I understand. So will it satisfy the conditions on V? So
Yes, sir.
you
It will
it it
return
it,
V.
it will return V when you apply V. Okay.
Yes, sir.
Okay. Okay. Any other guess? This is very interesting observation, Kshitij. Okay, I will come back to this observation. We'll see what we can do with what you just said. Okay, it's a very nice observation. But right now I don't want to go into that direction, so that's why I'm asking any other guess that you can do. You are, yeah. I'll come back to your construction, Kshitij. So suppose I say Q is equal to I minus 2P. Suppose I say Q is equal to I minus 2P. Is that okay? Does the Q that I construct like I minus 2P satisfy everything that I want Q to satisfy? So what do I want? We want Q of U to be equal to what? Minus U. Q of V to be equal to V. So let us check QU I minus 2PU, which is nothing but I minus 2 U transpose into U, which is equal to U minus 2 U transpose U. So this becomes 1. You get minus U here, U minus 2U, which is equal to minus U. And what happens to QV? QV is I minus 2PV, which is nothing but I minus 2U transpose V, which is nothing but V minus 2U transpose V. So this is 0. So you get a V here. So U is going to minus U, V is going to V. And is this matrix orthogonal? I minus 2P transpose I minus 2P. Correct? So I minus 2U transpose I minus 2U transpose. You can check this is equal to identity. So this matrix Q actually is orthogonal also, and it satisfies all the properties we wanted it to satisfy. So this matrix Q is basically a reflector. What is this matrix Q? This matrix Q is basically a reflector, and it reflects every vector through a line L. Okay, so what is the property of the line L? The property of the line L is first that it passes through origin, and that means that you are looking at a one-dimensional subspace of L. Okay, when it passes through origin, you are looking at one-dimensional subspace of L. Then how did you construct this reflector? The way you constructed this reflector is you chose the basis. What was the orthogonal basis for R2 that you chose? V and U. And what did you do with V and U? You just said the Q matrix, if it is reflecting, what should it do? It should do the following, right? So that's what it's doing. So if this is what we understand here, if this is what we understand here, then can we generalize this process to a Rn space? So instead of this line, what will I have? Instead of this line L, what will I have in Rn?
Hyperplane.
I will have a hyperplane, n minus 1 dimensional hyperplane passing through origin, right? What will I do for that n minus 1 dimensional hyperplane? What will I do? You choose an orthogonal basis. You choose, in fact, an orthonormal basis for that n minus 1 dimensional hyperplane. What is that basis? That basis is basically like V, the vector V, right? So you call that capital V with n minus 1 columns, and those n minus 1 columns are orthonormal to each other. Do you agree? That is how I chose V. And what is U now? U is a unit vector in this space, which is in the direction of normal to this particular plane. And these DRs, they are normalized DRs, right? The entries in U will be normalized DRs, direction ratios basically of that normal, right? So that is also a unit vector. Or if you don't understand this geometry, then U is basically a unit vector which is orthogonal to V, completes the basis into the basis of Rn, right? That's what you do. And then what do you want? You want this QV, same logic. The vectors in the plane should stay in the plane, and the vectors which are outside the plane should travel along the direction of normal through the plane equal distance. That's the reflection, right? That's what you are doing. So same logic, same equations, and the only thing that will happen is that now the matrix P and matrix Q that you construct. So this P will be UU transpose, and again the same logic. When you multiply any matrix V on the right, because U and V are orthogonal, you will get 0, and it will still represent a projection through this projection onto this particular plane, and you still can construct the matrix Q, which will be this. Do you agree? Do you understand geometrically what just I did here? Is this okay? I need a feedback at this point of time. Otherwise, I don't know whether I'm making myself clear or not. Is this process clear to all of you? This process can be generalized to Rn. And how do we generalize this process to Rn? Let L be an n-dimensional subspace. N minus 1 dimensional subspace of Rn. Let the matrix Q tilde, or let, I'll just say V1, V2 up to Vn minus 1 be an orthonormal basis norm of U is equal to 1, and U is orthogonal to the set, orthogonal to L. That's what I'm saying. Geometrically, what you are saying? U is a unit vector in the direction of normal, correct? To this plane L. Then construct Q such that, so construct orthogonal Q every x in Rn, Qx is reflection of x through R. So this is what Q will do. Okay, so for every x in Rn, Qx is the reflection of x through n. So I think you can construct this. So can somebody summarize what will be done? Once, can somebody summarize what will be done here?
Sir, why do we need orthonormal basis of L?
Huh?
Why do we need orthonormal basis of L, V1, V2?
We,
Yeah.
re we really do not need orthonormal basis of L. You can start with any basis. The condition that U is orthogonal to L is enough, and I want norm of U to be equal to 1. Okay, so norm of U equal to 1 is really very important. Otherwise, yeah, you are right. You don't really need orthonormal basis of L. Any basis of L. Yeah, so maybe orthonormal is optional. You really do not need it. Any other observation here? So now you will ask the question, like all these things are okay, but like rotators, are these reflectors also going to help us in introducing zeros in the vector or not? Okay, so our aim is to introduce zeros in a vector so that we can go to that triangular structure, right? That is what we really want to do. So how does reflectors help us introduce zeros in a vector? So what is it that we really want to do? What is it that really want to do? You have a vector x1, x2 up to xn. You want to apply this reflector q such that what happens? You get this star 0, 0, 0, 0, 0. Okay. Can we have, so this can be only one reflector, or this can be a series of reflectors, like we had series of rotators, and can we do something like this and achieve this particular transformation? So it can be a product of it can be a single reflector or product of several reflectors, and that is what we are trying to investigate. Okay, so this is the question that we want to answer, and we'll prove a theorem now which says that we can actually find a reflector which will do this job. Okay, so how will we do that? It's based on the concept of angle bisector. So simple vector addition understanding will help us to come up with the proof. Okay, so let us write the. Okay, so it's almost time. So maybe I will not start with this theorem now because it will take some time for me to explain. So yeah, maybe we'll stop here today. And coming back to question raised by Kshitij, I think what I will do is I'll put that question in the assignment. Okay. So assignment is coming anyway. So I will